but then the second one is going to be a little bit more complicated. So let's go ahead. If there's no questions, I want to go ahead and get started. Melissa says gross. Yep, gross. So I want to consider the idea that we have a point mass that is hung in such a way that it's right there, about a distance, we'll say this is a distance L, on some kind of, near the ground. And we are going to fire a dart into that point mass. There are a variety of ways this question can be asked, and I don't think that any of them are particularly crazy, so why don't you think about some of the things that would be asked here, like what velocity would cause an angle of theta, or if the dart becomes embedded, how high does the system swing upwards? There's a variety of ways the question can be answered. Let's, for just practice and to give you guys a chance to kind of flex your gray matter a bit, let's say this is M, and let's say that this is 2M, and that after the collision, the system rotates a distance theta with the dart sticking out here. So why don't you take about, 2 minutes and give me a relationship between theta and the launch velocity v. You can have M in your answer, you can have L in your answer, and you can have G in your answer. And that really should be it. Does everybody understand what I'm asking you to figure out? Do you guys want to have small little chat rooms for this, or do you think you can work it on your own? Put yes, I want small groups. No, I think I got it in the participant list. Not a particularly hard question. Should have been fairly straightforward, but I know some of you still struggle with this a little bit. So would anybody like to take the lead on telling me what the first thing was that you had to do? Okay, how'd you do that? Yeah, you're definitely going to probably need this if you want to get a relationship between theta and the other variables. So what would we need to do next after that? Somebody else chime in here. All right, so we have this intermediate thing that's not listed, that we need the velocity of the system after the collision. And how would you figure that out, Tyler? Fantastic. So we're really close to the end. Somebody else give me this last piece at the end here. Well, there's got to be somebody. Got a lot of folks there. I can just call you out. You don't want me to do that. Oh, that hurts my feelings. Makes me feel sad. So in the participant windows, it's because you don't know how to do it, or because you are unsure of your work? Yes, I don't know how to do it. No, I'm just unsure of my work. Kind of evenly split here. All right. So when Tyler found the velocity of the system right after the collision, what he's actually now done is he has found how much kinetic energy the system has right after the collision. The system is no longer conserving momentum because there's an external force acting on the system, and that force, is, in this case, is the tension in the cable. It's definitely going to slow the system down. That, combined with gravity, is going to slow the system down to a stop. However, it's a conservative force that's acting on the system at this point. Because it's a conservative force, we know that the net change in energy, mechanical energy, is zero. So whatever kinetic energy we have right here, that should be the total amount of energy after the cable swings upwards a small amount. Now, we got to kind of figure out where this energy is going, but we only have a couple of options, and I think the most likely option is that we're going to be storing this energy in the form of gravitational potential energy, suggesting that we can set the kinetic energy right after the collision equal to the gravitational potential energy when the system comes to rest. Remember, the system now has a mass of 3m. Not that I think that's going to matter, but I want to be careful because I got screwed all that up on Thursday. We know there's quite a record of all the mistakes I made on Thursday. Yes. And it's okay. It doesn't hurt my feelings all that much. But it is appropriate that we say that we have 1/2 times 3m times 1/3 v squared. This is the amount of energy we have, kinetic energy, after the collision in terms of the variables that were given. Any question about that? I can't have h. I'm trying to find a relationship between theta and the variables. So the first thing I should do here is write this as 3mg times L times 1 minus cosine theta. Pulling down this substitution. And this is still going to be, and I can clean this up a little bit, but I'm just going to write it all out because I know some of you need to see this, and some of you are going to be in a world of hurt when we have our live test if we don't pick up the pace there a bit. I can come through and cancel out the 3m's. And if I'm really trying to get this in terms of theta, I should probably get and collect the variables. So on the left side, I have 1/18 v squared. So as an intermediate step, on this side I'll have GL times 1 minus cosine theta. Now, no, I think the 3m's cancel on both sides. That's right. One of the interesting things about this problem is that we are going to get theta, as part of our answer. And clearly we could get theta by itself if we want. I'm not sure if that exercise is particularly interesting, but getting theta by itself would at least demonstrate that m didn't contribute to the answer in a meaningful way. At least that's how it appears, and that would be a lie. I want to be very clear, m does contribute even though it's not in the answer. Can somebody tell me how m contributed here? Like, where was the contribution of the mass in this system? That's right. The 1/3 we get here is purely based on the fact that the masses were related to each other. One object was twice as massive as the other. The reason it cancels out in this problem is because of that and that alone. If this had been lowercase m and this had been capital M, we would have some fraction, probably indicating the ratio of the masses somewhere here in the problem. But the fact that we made the masses multiples of each other is why the mass cancels out in this problem, not because of conservation of energy. That's not it. And I want to be very clear. The mass only cancels out because we made them multiples of each other. This 1/3 is the last remnant of that, which is in the middle of this fraction here. And it represents how those masses were related during the collision. Now, this in and of itself isn't the problem that I'm most interested in. What I'm most interested in is how this problem relates to a more contemporary problem with our knowledge base. We have a more advanced knowledge base now. And because of that, we should be able to do a more contemporary problem. So before I leave this is supposed to be more like the basic problem. Are there any questions about this? Because what we're going to look at next is a little bit more complicated. All right, I got nothing in the participant window, no hands raised in the little boxes. So let's just done. Can you do that from the standpoint of angular momentum as well? We did it from the standpoint of linear, but could you do it from the standpoint of angular? And I'm going to tell you, the answer is yes. We could have done this whole problem using all angular momentum and angular relationships. I'm not sure it's easier or harder, but take a look at this. And this is not a big change. I'm going to try and keep this relatively straightforward, but what happens when instead of us having a box down there, we have, say, a bar of length L, mass 2m, and we have this dart traveling at v, mass m, that's going to strike the bottom of the bar. Now, without doing any calculation, do you think this will increase the angle after the collision, decrease the angle, or will the angle be unaffected? I would love to see 26 answers in the chat. Increase, yeah. In this, if we replace the mass on a string with a bar of the same mass, will this increase the angle we get, decrease the angle we get, or will the angle be unaffected? Well, that's not quite 25 answers, but it's approaching it. All right, let's just consider a couple of simple questions that you could have asked yourself in trying to figure this out. And we want to go back to big banner topics. Things like inertia, force, energy. What changed? Did the momentum of the system change by replacing the mass with a bar? No, my initial momentum is still the same. Now, we don't know what's going to happen during the collision in regards to the energy. We know energy was lost in the last collision because it was inelastic. The question now, though, is what has changed about this system compared to the other one? And in asking about the angle, we're trying to figure out which one of these systems is easier to turn. Was the other system easier to turn, or is this system easier to turn? And Wes says moment of inertia. So, Wes, do you mean the moment of inertia increased, decreased, or stayed the same compared to the prior example? So, the prior moment of inertia when we had the mass on the string. This object's moment of inertia is 2ml squared. Right? The mass in the string would be treated like a point mass. And that would have to be what we'd consider to be the moment of inertia of that system. What's the moment of inertia of our new system? All right, so the coefficient for a bar about its end is 1/3 times 2m. Yep, so I'm seeing that we'd have a clear decrease in moment of inertia. And not a small decrease. I'm thinking that's a pretty hefty decrease in the moment of inertia, suggesting that the bar is going to be easier to turn than the mass on the string. My expectation is that this should produce a larger angle than the prior example. And that's your job for this evening. I actually have 2 jobs I'd like you to do this evening. And if you want me to consider perhaps, I don't even know how to say this. I'd like to see the work on it, but just to see if you're having trouble with it. So I'm not looking for you to submit it through ESBI or anything like that. I think if you're having difficulty, you should really come at me tomorrow morning and try and get your questions answered. But I think you should do 2 things tonight. First, I think you should compare the 1 minus cosine theta from the prior example with this example. To solve for cosine, just compare the 1 minus cosine thetas. Because what we're really comparing then is h in both cases. The one with the bigger h should be the one that was easier to turn. Second, though, we did the problem from the standpoint of linear momentum. Now, you are not going to be able to do that here. You're going to have to use angular momentum in order to make this calculation. So my question for you is, I'd made the whole second part of this about moment of inertia. Well, can you do this problem? The one you should definitely consider perhaps working out what it would look like to try and do it as an angular momentum problem instead of a linear momentum problem. I'm not asking for much. Maybe spend, 15 minutes after we're done here sometime during the course of the day trying to work this one out. That's what I would like you guys to do before tomorrow. And of course, maybe start looking at my AP. And there's a couple FRQs I think you should take a look at. When I put a few practice FRQs out there, what I'm really trying to tell you is the kind of question I'm leaning towards for your live quiz on Thursday. Does that make sense? That's why I posted them. Those won't be the ones you're going to get, but I'm leaning towards ones that look like that. All right, guys. I posted a message in Slack about having to choose the Physics Student of the Year. Please take a read on it. I have to make a decision by 1 o'clock this afternoon. I've got my short list, but I know how I feel about the whole thing. And I didn't get a chance to talk to you guys about it too much this morning, but it does involve, people like you. And I'm just looking at the names that are right now, on this list. And there's a lot of you who are excellent students and are very deserving. It's hard to try and narrow it down to this year I only get to pick one. So keep in mind that I'm thinking about many of you and your contributions over the course of this year. And it's really hard for me to settle on just one person. But I have to do it by 1 o'clock today. So it's weighing on me heavily. I'm just throwing it out there. But you guys have a fantastic day. It's good to see 6 of you. And it's good to hear from 8 of you. And I hope the other 20 of you have a fantastic day as well. It's good to see at least your names showing up in the list. So have a wonderful day, guys. I look forward to seeing you all tomorrow morning. And I don't know, I'd say go out and play, but it looks kind of cloudy and kind of oof out there. But, maybe it'll be a nice day to go outside and play. Who knows? I'm going to try and do so when I'm done with all of this today. So see you all later. Have a great day. And I'm glad you could make it to class today. Bye, guys. It was good to see you all.